And now, let's look at one example. A thin horizontal bar of weight 100 Newton and length 2 meters is hinged to a vertical wall at one end. Okay. So you have a vertical wall like this. We have a hinge here. You have a bar like this. Okay, the other end is supported by a thin wire that makes an angle 30 degrees with the horizontal. So, of course, you need to support the other end. So it says that you are support the other end like this. You have this wire here, and the wire makes a 30 degrees like this. A block of mass 200 Newton is placed on the bar with a distance 0.5 meters from the wall. So you have block here. We want to find the tension in the wire. Find the vertical and horizontal components of the force of the and the hinge of the on the bar. Okay. So what we're going to focus on. Okay. So at the beginning of the problem, you need to know that we have to analyze the bar. Okay. And there are many forces acted on the bar. First, it has its own weight. It's given 100 Newton, right? Another one, because we place a block here, so the block will produce some pushing force, okay, on the bar, which is the same as the weight of the block. So you have a 200 Newton pushing force on the bar here, right? And there are some supporting force for the bar. One is the tension here. Okay. And also you have the supporting force on the hinge. This force should be, in general, should be in some arbitrary direction. Okay. It may not vertical or horizontal. So this force will have both x and y component. We need to calculate both. So let's say you have some, let's call this nx. Okay, this one is ny. So in general, it may have two components. The force itself may along this direction. Okay, and this one, let's call it w1. This is w2. Okay, this is w1. This is w2. So that's the force analysis for the bar here. Any question? So together we have totally 1, 2, 3, 4, 5 forces. Okay? Now, then we have to write down the force balance equation and the torque balance equation here. Usually we start with the torque balance equation. Okay? So, to write down the torque balance equation, please note that. So that says that this object tries to rotate, but it's not in rotation. There is no actual rotation. So it produces some freedom for us. If you have some actual rotation, then you know where is the rotational center, right? But here, the object, the bar, tries to rotate, but there is no actual rotation. So in that case, you don't have some real rotational center. You can choose any point to construct some imaginary rotation. Okay, you can choose your rotational center in this case. Okay? So there is an issue. That means once you can choose something, then you may have some good choice or bad choice. Okay. So what is the best choice for the rotational center in this case? You think about the bar. If you try to construct some imaginary rotation for the bar, where should be the best rotational center you would choose?
Underneath the block. Underneath the block.
Underneath the block here? Okay, so that's your choice. Any other choice?
Where the string attaches.
This one? Okay, anything else? The hinge. Anything else? Okay, I tried to run all the possibilities. Maybe you already got the right one. So, of course, okay, you are in the right track. There must be some, you cannot just choose it as an arbitrary point, right? There must be some, like here, the hinge here, this edge, someone say this one, or another one may be the center, okay? You need to choose from one of these spatial points. But the best one, I would say, this, the hinge. Okay. So, I will illustrate why this is the best choice. Okay, when we go through the procedure. First, let me tell you, that's the best choice. And now I'm going to write down the torque equation for this imaginary rotation. If you think about this is your center. So all these forces will produce some, we'll try to make some counterclockwise or clockwise rotation. So they produce some torque. So, okay. That means all the torque together, if there is no rotation, all the torques together will be balanced. You have 5 forces. Each of them may produce some torque. So in general, you have 5 torque, right? We call them torque produced by the normal force Nx, okay, the torque produced by normal force Ny, the torque produced by W1, the torque produced by W2, the torque produced by tension T. All of them together will make 0. That's a torque equation in general. Okay. Now, what we are going to see is that, let's try to identify 0 torques. How can I identify 0 torque? Remember what did we see? What did we see there? If a force, what kind of force will always produce 0 torque?
Because it's the center of rotation.
If the force goes through the center of the rotation, the torque will be 0. Okay? Is any force goes through the center of the rotation?
Why?
How many forces goes through the center of the rotation?
2.
2. So the torque produced by this and by this will be 0. Okay? Can see that this is kind of support us why this is our best choice, because there are 2 forces go through here, right, in this equation. And by the way, more importantly, this Nx and Ny are the unknown force, right? So if the torque produced by Nx and Ny will be 0. So the 2 unknown forces, Nx and Ny, they will not appear in this equation. So in this equation, you have only one unknown force, T. So without the help from other equation, you can directly solve for T from this equation. Okay. That's a good thing. You can think about, for example, if you choose this as your rotational center, so this term will go away. You still have 4 terms here, and you have 2 unknown quantities. So itself you cannot solve for any unknown quantity. You need to combine it with the 4th equation. Or if you choose, like say, this one, as your rotational center, then which term will go straight? This term will be 0. Now you have this equation, this term, this term, this term, this term, but you have 1, 2, 3, 3 unknown quantities. Again, you cannot solve it by itself. So you can see this choice will simplify your problem a lot. Okay? Any question here? So when you choose imaginary rotational center, you try to choose a point where you can kill many unknown forces. So if there are many unknown forces go through that point, you should choose that point as your rotational center. Any question here? Okay, so that's the first thing. Choose a good rotational center so you can kill some of the forces. Another thing is that we have these tops together. If you add these tops together, it should give the 0. But see that I didn't put the positive side, the addition side at the beginning, because I want to make sure are they positive or negative. Talks can be positive and negative, right? So about this rotational center, is tau W1 positive or negative? About the center.
Negative.
Negative, right? About the center, it will produce some clockwise rotation. How about tau W2?
Negative.
Negative. Again, it will make some clockwise rotation. How about tau P?
Positive.
Positive. Okay. It will make some counterclockwise rotation. So negative, negative, positive. Okay. So that's another thing you need to pay attention to. Now, then we want to try to calculate the tension T. We can just expand each term to relate them to the force. For torque, you can always use R perpendicular multiplied by that force. Okay. So you get from negative R perpendicular, let's go R perpendicular 1 multiplied by W1 minus R perpendicular 2 multiplied by W2 plus R perpendicular, let's call it R perpendicular T multiplied by tension T equals to 0. Okay. And we need to figure out all these perpendicular distance. Perpendicular radius, then we can calculate the tension T. Okay. Now let's look at what is R perpendicular 1. The perpendicular radius for the weight from the center. What's that? Okay, tell me the number. The length of the bar is 2 meters. So what is this? The R perpendicular for this one. 1 meter. In this case, okay, it equals to 1 meter, right? This was R1. W1. How about R perpendicular 2? 0.5. Let's go to R2. Okay. Here is R2. Here is R1. R2 equals to 0.5 meter. Multiplied by W2. Okay. So here can you see that we can easily figure out the number for this R perpendicular, because in this case R perpendicular equals to R, right? Because these forces are perpendicular to the radius direction of the bar. But for the tension T, will not be that simple. Okay. On the graph, where is R perpendicular? How does the R perpendicular looks like for the tension T? Or can you directly tell me the number? Okay. Can you see that the R perpendicular for the tension T should be, you try to figure out the distance from the center to the straight line of the tension. So the distance from the center to the straight line of the motion should be this. This is R perpendicular T, right? Okay. But we can still figure out why is this. Okay. So R perpendicular T equals to, how can we calculate this distance?
Trig stuff. Trig magic.
Okay. How would like to calculate the distance here? Perpendicular. Look at the triangle. So it should be the hypotenuse multiplied by sine 30 degree, right? So 2 meter multiplied by sine 30. Any question here? Okay, so sum of the lever arm, you have to calculate it. So this is actually 1 meter. Okay, so -1. So R perpendicular 2 multiplied. -1 multiplied by 100 minus 0.5 multiplied by 200 plus 1 multiplied by t equals to 0. So t equals to 100, 200 Newton, right? Okay, any question here? Please note, what is the R perpendicular for different force here? Okay? Now, once you calculated the tension T, you can go further to calculate now the two forces, Nx and Ny. So we already used the torque equation, so we still need to use the force balance equation to calculate Nx and Ny. If we want to calculate the Nx and Ny, okay, let's look at all the forces. You have W1, W2, Ny, Nx, okay? And now we have tension T here, T along this direction. So for the force equation, you want to write the equation along x direction and y direction. So obviously you want to decompose the tension T. Okay, to get this is Tx, this is Ty, right? So of course it should be easy because this is 30 degree. So Tx equals to T multiplied by cosine 30 degree. Ty equals to T multiplied by sine 30 degree. So this is 200 multiplied by 0.5, so it's 100. Ty equals to 100. Tx, what's Tx? T multiplied by cosine is 30, what's that? 200 multiplied by cosine is 30. Cosine is 30. 200 multiplied by cosine is 30, what's that? 173. Okay. So that's Tx and Ty. Now, you can see if we write down the x direction force balance equation, it should be, how many forces do we have along x direction? 1, 2, right? So it should be Nx minus Tx equals to 0. So of course that means Nx equals to Tx equals to 173. And along y direction, you should have Ny plus Ty minus W1 minus W2 equals to 0, right? So Ny plus 100 minus 100 minus 200 equals to 0. So Ny equals to 200. Okay? Any question here?
Could you just explain it from the top again? You just started doing something.
Not once.
Not this guy.
Okay, yeah, first you have all these forces here, right? Here we just calculate the torque produced by all the forces. Now, we just want to calculate the net force produced by all these forces. Remember, how can we, the force analysis, if you have all these forces, you decompose them into x and y direction. Calculate the net force along x direction, which is nx minus tx, right? That's the net force along x direction. This should be 0. Our torque equation should be F net x equals to 0. Or not torque equation, force equation, right? And then you calculate net force along y direction and set it to 0. Right? Force? All this force are plotted here. Okay?
I'm gonna say NX equals TX equals 170.
Nx minus tx equals to 0. That's the equation. And then, of course, nx equals to tx, right? By solving this equation. Any other question? Okay, you can see here, the calculation starts with the torque equation and then goes to the force equation. That's one thing you pay attention to. For the torque equation, there are several things you need to pay attention to, like how can we calculate the R perpendicular for each force.